All right, so we're going to be looking here at empirical formulas. So there's two types of, when you're reading a formula, two types of formulas that something could be, either empirical or molecular. So we're going to talk about the differences between the two, and then we're going to look at how to go about calculating empirical formulas. So first of all, empirical formulas are the lowest number ratio that atoms can have in a compound. Molecular formulas are sometimes also referred to as being the true formula or the real formula. So molecular formula tells you exactly how many you have of each element in a compound. Okay, so here the best way is to kind of look at an example. So let's say we have a real formula of C6H6. Well, this is not reduced, right? So this is the real molecular formula for that compound. An empirical formula is if we were to take that and reduce it down into the lowest ratio possible. So 6 and 6 would essentially become 1 and 1. So the empirical formula is basically the original real formula, but reduced down, okay? Now, this value, this here, where it's showing you empirical formula to an n factor, is basically just telling you, well, what did you essentially reduce it down by? So the molecular formula was C6H6. So if I wanted to go from the empirical formula back to the real formula, I'd have to multiply all of my subscripts by 6. Okay, so I'll give you another example. So even like we'll just make something up here. So let's say I had X4Y2, and this would be the molecular formula. When we reduce this down, it would be X2Y1, right? That would be our empirical formula. So the factor that we reduced this down by was 2. So my empirical formula multiplied by 2 would get me back to that original real formula. Okay, so that's kind of what how you have to look at this n factor. It's saying, what do you multiply the subscripts by to get to the true formula for the molecule? So sometimes you already have the empirical formula. So for example, ionic compounds. We know that ionic compounds, after you do the crisscross rule, you have to reduce to the lowest ratio. That's part of the rules of creating ionic compounds. So ionic compounds are technically both the real formula and the empirical formula. Like they're the same thing. So for example, sodium chloride, right, it's 1 and 1. Magnesium chloride, 1 to 2. Like you cannot reduce these down any further than they already are, because they're already reduced. That's part of the nature of the ionic formula. So for molecular compounds, remember non-metals only, sometimes they might already be their lowest ratio, but not always. So for example, water, remember molecular formula is the true formula for the compounds. So here, water is already in its lowest ratio. It technically is both the molecular formula and the empirical formula. Okay, but let's check this out. So here we have C6H12O6. So this is glucose. So glucose has the possibility of being reduced. So the empirical formula here would be CH2O. So if we had to apply the factor to this to go backwards, it would be 6. Over here, we happen to have, I believe this is sucrose, but anyways, we have carbon 12, H22O11. So in this case, you cannot reduce them down. Even though you have 2 out of the 3 that can, it doesn't matter. It's everything or nothing. So in this case, this is similar to water, right? This cannot be reduced down. So it's almost like you have a factor of 1. It's already the same. They're equal. So what we're going to talk about today is basically, if we have data about a molecule, is there a way that we can calculate the empirical formula? So the answer is yes. So actually the only thing we require to have, what we must have, is the percent composition. So we've learned about percent composition already. we have to have percent composition in order to figure out the empirical formula. And you're going to see, we're going to do some examples together. I'm going to have you try one out on your own. So this slide right here basically goes through the steps we're going to do. They're not going to make a lot of sense right now because you have to kind of see examples and practice this in order to really understand what's going on. Okay, so number one, we're going to base our calculation as if we had 100 grams of the sample. Number two, we're going to find the moles for each element. We're then going to divide all the moles by the smallest number of moles. Again, this is not making a lot of sense right now because you have to see it happen. And then we're going to multiply each number by an integer if needed. So this last step is if needed. We may or may not need this. Okay, so let's start taking a look at what the heck am I saying. So we have adipic acid contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. So they're giving us the percent composition. What is the empirical formula of adipic acid? Okay, so here are the steps. Number one, we're going to treat it as if we have 100 grams of that substance. So what that means is we're going to basically take the percentage. So we're going to pretend that the mass of the total thing is 100 grams. Okay. Well, if we know we have 49.32% carbon, if we had 100 grams of it, basically that would mean I would have 49.32 grams of carbon. Like by assuming we have 100 grams, we're essentially taking the percentage values and making them our mass value. Because remember, percent composition by mass never changes. It doesn't matter if you have 100 grams or 10,000 grams, it will always be 49.32% carbon. So what that allows us to do is we can now assume that the mass of our carbon is now 49.32 grams. The mass of our oxygen is 43.84 grams. And the mass of our hydrogen is 6.85 grams. Okay, so we have our mass values. All right, next, we're going to convert the mass values into moles for each element. So we're going to have to solve for, and it's very important, especially now. Remember, we've kind of gone to the habit of labeling with our little subscript what the mass is for each thing, like which elements these are for. So now this is going to become important because we're going to have a whole bunch of different mole values also. So we're going to have to solve for the moles of carbon, moles of oxygen, moles of hydrogen. So we're going to do that by doing mass over the molar mass, right? So it's going to be 49.32 grams over 12.01 grams per mole. Remember, we get that from the periodic table. So we get 49.32 divided by 12.01. So we get 4.1066, let's say, moles. So remember, you don't want to really round this. Don't round this to 4 moles. We're not done yet. So we got to keep it, you don't have to keep all 9 decimal places, but you don't want to round it too much either. Okay, so moles of oxygen. We're going to do our 43.84 grams over 16.00 grams per mole. Okay, so 43.84 divided by 16. So we get 2.74 moles of oxygen. And then we got to do our moles of hydrogen. So that is 6.85 grams over 1.01 grams per mole. 6.85 divided by 1.01. So we get here 6.782 moles. Okay, so we have 3 mole values. Right, so we have moles of each of our elements. So it doesn't matter how many elements you have. There could have been 5 elements. You find the moles of each one. So now the next step says divide each value of moles by the smallest of the values. So what that means is whichever one of these is the smallest, so in this case it's our oxygen, we're going to divide each mole value by the smallest number. So I'm going to do 4.1066 divided by 2.74. I'm going to do 2.74 divided by itself, and then 6.782 divided by 2.74. What we're doing, what we're trying to accomplish with this next step is we're trying to figure out the ratio. For every one oxygen, how many carbons do we have? For every one oxygen, how many hydrogens do we have? So let's do that. Now I have to remember these numbers. So we have 4.1066. So here we go. 4.1066. Was it a 1 or 0? Ah, thank goodness. Moles divided by 2.74 moles. Right? So our smallest value is oxygen. So what we're going to do here is we're going to get a value. 1066 divided by 2.74. So here we get 1.499 basically. Okay, there's no unit actually for this because the units of moles cancel. Okay, so hydrogen, oxygen, why don't we do this because I remember this number and it's divided by itself, which is nice and easy, which is going to be 1, right? And then hydrogen is 6.782 divided by 2.74 moles. So we got 6.782 divided by 2.74. So this is 2.475. Okay. So what these numbers represent right here are essentially the subscripts. So carbon is 1.5 carbon, right? Let's round that. Hydrogen, we have 2.5 hydrogens and we have 1 oxygen. So when you're doing this, the answer you get after you divide out your moles to get your ratio, those are essentially representing your subscripts. Now, have you ever seen a subscript with a decimal point? No, you haven't. Okay. So if you remember, I told you that the last step in this was only if needed. So it says we're going to multiply each number by an integer to obtain all whole numbers. So let's say we were to do this, okay, and this is an important point. If you're calculating your ratio here and it's within 0.1, okay, so what I mean by that, let's say we solved for, let's do imaginary numbers. Let's say x, y, and z, okay? So let's say after we divide, remember you're dividing your 2 moles. So let's say z ended up being 1. Y was 9.9 and X was 8.1. If you're within 0.1 of a whole number, you can round this to a whole number. Okay, so meaning my formula would be X8, Y10, and a Z. Only if within 0.1. Okay. I cannot round a 0.5 up. It's too far off from a whole number. It's going to disrupt my ratio. So this is why I say if needed, because if the answers you get here are whole numbers, basically you're done. But in this case, they're not whole numbers. So what we have to do is we have to multiply by something to get these to be whole numbers, and you have to multiply it by everything. So in this case, because it's 0.5, we can multiply by 2. So carbon, 1.5 times 2 is a 3. 2.5 times 2 is a 5. And oxygen would be a 2. Right? So this would be our empirical formula. So let's review what we did. We assumed we have 100 grams. So you make your percentage into a mass. You find the moles of each element. You find the ratio of each element's moles by dividing by the smallest number. And then if you need to multiply to get them to be whole number subscripts, you would then do that. Okay, so actually that's what this next step is here showing you, but we did that on the last slide. So if needed, right, you multiply each number to obtain whole numbers. All right, we'll look at another example in the next part.